Good morning, my name is Mattia Fumagalli from the Conceptual and Cognitive Modeling Research Group, University of Bolzano. The work I'm going to present you was done in collaboration with Tiago Prinsales and Giancarlo Guizzardi, and its title is Mind the Gap: Learning Missing Constraints from Annotated Conceptual Model Simulations. In this presentation, first we are going to introduce you to the context in which our proposal is framed. Secondly, we will give you a brief description of the problem we address. Thirdly, we will describe the key aspects of our solution. And finally, we will discuss a list of next steps we are going to address. The work presented in this paper falls in the general area concerned with the development of artificial intelligence techniques for the enterprise. Loosely speaking, the long-term goal in which we frame the work is targeting improvements to existing engineering tools and methodologies in order to better support the construction and the validation as well of conceptual models or ontologies for enterprise. More specifically, the main focus here is on how to help engineers in avoiding unintended model instantiations or configurations, or simply models of a given conceptual model. Here it is important to notice that we use the terms model instantiations, simulation run, and configuration as synonyms, where a model instantiation or simply a model is the result of an interpretation function satisfying the conceptual model. Avoiding unintended model configurations could be a tricky issue. It is not indeed about syntax checking. It is not about satisfiability checking as well. But it is about checking if, for instance, A Mary and B Mary is okay with what we meant by designing the conceptual model, where A and B could be two simple predicates like professor and student, and we have to check whether we want or not that Mary is both a professor and a student. Let's provide an example to be more clear. Suppose we have the following simple model in standard UML, where we have three classes, namely a parent class, like person, and two subclasses, namely woman and man. Now, suppose we can look for the configurations admitted by the model with at most two instances. These are all the possible options for this simple model. We may have the case like in A in the picture, where we have a single instance of man. We may have the case like E in the picture, where we have two instances of just a person. We may also have the case like in H, where we have an instance that is both woman and man, and an instance that is a person. Now, suppose that by looking at these configurations, we identify some intended and unintended outputs. Like, for instance, we may admit that an instance is just an instance of woman or just an instance of man. We may want to avoid that instances are both instances of woman and man, and we may even admit that two instances are two instances of the same class, man or woman. So what if we want to avoid the not admitted model and all the cases in which persons has a direct instance and where an instance is both a man and a woman? To avoid the unintended instantiations, of course, we must understand the problem and then fix the source model. In this specific case, to fix the problem, we should put an axiom and constrain the source model. This axiom should state that every person is either a man or a woman, and no person is both a man and a woman. And here is the challenge we are addressing. So, what if from the highlighted intended and unintended models we can automatically learn some patches or axioms for fixing the source conceptual model? And let's say also possibly automatically repair the conceptual model according to these patches? This is widely recognized as a very helpful support in conceptual model design, especially in the context where designers have no high-level expertise and have to deal with very complex models. Here is an overview of our proposed solution. As you can see, the whole framework can be divided in two blocks of activities: the simulation block and the induction block. The simulation block is divided in two phases. The first phase is the generation phase, where we have a model conversion step and a model finding step. The assertion phase, which is the second phase of the simulation block, is composed by an annotation step and a populated model generation step. The induction block is in turn divided in two phases as well. The preparation phase, where basically we set up the ILP task, and the learning phase, where we derive the rules that we use for constraining the input conceptual model. To show how the approach works, let's take this example of model, which is actually a view of a OntoUML model, but can be seen as a UML model extended by stereotypes. Here we have classes, specializations, and a composition relation with cardinality constraints. This model allows for the following potentially not admitted instantiations. We may have vehicles that are neither cars, boats, nor airplanes. See this generalization set where we don't have the property of disjointness and completeness. We may have vehicles that are both cars and boats, but not amphibious cars. We may have vehicles that have no engines. As shown in the overview of the process, the generation step has a key value, especially to highlight these issues by applying a converter that transforms the input model into alloy specifications. This converter is a customization of the approach provided by previous works. For all the links to the data and processes used in this work, please check the full version of the paper. In the assertion step, the output of the generation step is processed. Here, the alloy analyzer APIs are applied to automatically analyze the model. The main step is to cluster all the output configurations into intended or unintended. Take, for instance, this example configuration. According to what we said about the input model, this can be an unintended configuration. Top 2 is indeed both an airplane and a car. In the preparation phase, the main steps are to generate a model populated by a set of instances coming from the intended and unintended simulations generated in the previous phase, which is the assertion phase, and to transform the populated model for the ILP setup, by also providing additional input about negative and positive instances. To generate the populated model, another transformation is applied. Again, for checking how this process works in practice, please check the full version of the paper. The learning phase is mainly about setting up the ILP task. Here we have an example of a part of the populated model transformation for this particular task, reusing the car simulation output that we showed above, along with the negative and positive examples. You can see indeed the negative and positive instances and the schema used as input to the ILP process. Once the data is derived and prepared, the ILP algorithm is ready to induce the constraints. Here, a list of outputs we were able to derive for the input example about vehicles. For instance, for the unintended configuration, which allows for some vehicles that are neither cars, boats, nor airplanes, we selected negative examples that are vehicles that are neither airplane, nor boat, nor car, and we derived the following rule. For the unintended configuration allowing for some vehicles that are both cars and boats but not amphibious cars, we provided negative examples where instances are both cars and boats but not amphibious cars, and the derived rule was the following. Finally, for the unintended configuration allowing for some vehicles that have no engines, we provided negative examples where vehicles have no engines, and we derived the following rule. As first implementation of the approach, we adopted DL Learner, which is a well-known state-of-the-art ILP framework. This is why the outputs we showed you above were both in description logic and first-order logic. DL Learner indeed produces rules which are encoded in description logic. However, many ILP approaches are available, and our goal for the immediate future work is to test multiple options and see what kind of constraints can be learned and what is the level of accuracy of all these options. As brief resume, we want to highlight some key implications related to our approach. First, the automatic conversion to alloy and the automatic generation of repair suggestions turn out to be useful allies in the conceptual modeling process. Second, the approach we are proposing allows storing and keeping track of information that may be lost during the runtime analysis, especially in the model validation phase. Third, the approach we are proposing allows to pave the way to a large number of case studies, especially on the application of different learning approaches. Finally, we can leverage a very small amount of data for generating the rules we need by implementing ILP algorithms. Given the promising results we had with this first work, we have multiple challenges to be addressed in the future. We highlighted 4 of them as the key challenges to be addressed in the immediate future. The first one is to learn constraints which are valid across domains, not only within a single domain of information. The second one is to generate a huge database of intended and unintended models to be used for validating even multiple ILP approaches and for running multiple case studies or trials. The third one is to use part of the process that we implemented in this first work to identify error-prone structures across conceptual models, so fragments allowing for unintended configurations, actually. The fourth challenge is to put this framework in the crowd, basically, to allow multiple people providing feedback and inducing rules which can be weighted according to a kind of process of negotiation of what is intended, what is unintended within and across domains of information. Many thanks for your attention. Looking forward to your feedback and questions.